Here's a strange way to start thinking about huge numbers. The biggest ones in your life might not look big at all. 0 to 1 is enormous. It's a jump from nothing to something. 2 can feel overwhelming if it's the number of kids you suddenly care for. And 3, sometimes 3 is exactly where things fall apart. So this isn't about how big is. It's about how big for whom and under what system. In Huge Numbers, Richard Elwes shows how huge numbers are really about context, limits of our intuition, our language, our notation, and even our computers. Science constantly forces us to talk in extremes, particles absurdly small and distances absurdly large. And the surprise is that the tiniest and the hugest numbers are inseparable. Ask how many protons make up a gram, and suddenly you're buried in digits. This book is about the numerical tools we've built to stretch human thought and the moment that those tools fail, because that's where the most interesting numbers live. Not just big numbers, but signposts marking the edge of what human thinking can handle, and where something stranger begins. I'm your host, Autumn Fnaf, and joining me today is Richard Elwes, professor of mathematics at the University of Leeds and Holgate session leader for the London Mathematical Society. So you start the book with the smallest scale, 0, 1, 2, 3, and then you go into subitizing. At what point was this a tipping point for you when realizing that the book wasn't just about numbers, it was about limits?
Yeah, I think that was quite early on. It was while I was really planning the book that I guess I had a realization at some point when I was planning a book project. My mind was sort of split between two different things at that point. So at that point, I was teaching a module in the history of mathematics, and we were looking at various ancient numeral systems, ancient Egyptian one particularly. And then I was also thinking for other reasons about some quite subtle ideas of modern mathematical logic. And I found some sort of unexpected point of contact that I wasn't really expecting to see. And that is that in both cases, if you push the numbers big enough, the system starts to creak. So in many ancient numeral systems, and ancient Egyptian is one. Roman numerals are probably the one that people are more familiar with. Roman numerals have got a pretty clear cutoff, right, as to how big a
Yes.
number you can write. I mean, if you want to write, a number in the millions, billions, trillions in Roman numerals, I mean, you basically can't do it. And the people who in the ancient world did find they needed to write very much bigger numbers had to just come up with. They had to basically invent new ways to extend those systems. So it's got a clear sort of limiting point. And I was finding something slight. I mean, it's not exactly the same, but in modern mathematical logic, there's similar things happen in that we've got different axiomatic systems. So I'm jumping up in the mathematical complexity a little bit here, but
That's all right.
I know the audience are here for some more crunchy math. So it's really about mathematical logic where we get the really biggest numbers in modern maths. And it comes from trying to write down the axiom scheme for maths. In other words, if you write down the sort of fundamental laws for arithmetic. So arithmetic here is just the whole numbers with addition, subtraction, multiplication, division. So it's not nothing particularly complicated, you would think. But if you try to write down the fundamental laws that make that tick, what you find is there's something like a speed limit is in terms of how fast growing a sequence of numbers you can handle. So the sort of standard axiom system was developed in the 19th century by Giuseppe Peano, who's an Italian logician. And Peano's axiom system remains the sort of standard one today, but you can break it by basically finding ways to define mathematical processes which just grow too fast for it. It's not one number isn't going to break it, but if you've got a sequence of numbers which grows fast enough, that axiom system will not be able to handle it. And so I found this sort of similarity between what the people in the ancient world were finding with their numeral systems were just literally ran out at some point. And what we find in mathematical logic now, that there's a sort of, again, a limit of a kind. And the common theme is huge numbers. And I thought, well, that seems something worth investigating.
Now, early on in the book, you take us back before language and before writing, and that's even before humans. Now, why does the story begin with animals and not just people?
It begins with animals because the fundamental tool that we use for any kind of numerical work is the human brain. And the human brain did not arrive fully formed, right? It
Correct.
evolved from previous versions, and we are related to other animals around the animal kingdom. And I thought it would be interesting to see to what extent our sense of number is shared with other animals around the animal kingdom, partly just out of interest, but also because that's indicating how far back it goes in our evolutionary history. And it actually goes back a lot further than you would expect. And that's so subitizing that I was talking about earlier is something we see in lots of different animals, not only mammals. So this is like quite a deeply evolutionary ingrained thing. And it's funny to think of non-human animals as having a sense of number because, of course, what they don't have is notation. They don't have words for numbers. So you might think, okay, they have no concept of numbers at all, but do have a sense of number which allows them to distinguish 2 from 3, for example. Even newborn chicks, baby chickens just hatched, can make this kind of distinction. And I thought it'd be interesting to see how far back it goes. And I was amazed how broadly these kinds of sense of number are shared across the animal kingdom. So subitizing is one. The other kind of sense of number one sees in different animals is related to larger numbers. And so with larger numbers, subitizing, we can spot the number exactly, right? We can just tell it's 2, it's 3, or whatever. With larger numbers, we can't do that. But what you can do, if I showed you like if I put 2 sets of coins on the table and I say, Autumn, which one's got more? If one's got 40 and the other's got 20, you're not going to be able to identify the number just by looking at it. But you will be able to tell me which is bigger.
Correct.
And that's the term people use for this is relative numerousness. And relative numerousness judgments are things, again, we see animals across the animal kingdom being able to make. So some experiments that people have done, for example, involve fish. And you can get, you put a small fish in the center of a tank, and the tank is divided into 3 chambers, so it's in the middle one. And if you put 2 small shoals of other fish of the same species on either side of it in the 2 side chambers, and the partition between them is transparent. So the principle of safety in numbers will lead this central fish to want to join one of the other shoals, and it should join the larger one.
Yes.
But to join the larger one, it needs to be able to tell which the large one is, right? So this is a quite an ingenious experiment for telling whether fish can tell the difference between 2 shoals of different sizes. And if they're very close together, if you've got 11 in one and 12 in the other, then the fish can't do it. But if you've got 10 in one and 20 in the other, then it can easily. So there's there's some sort of cutoff there, some number sense which is emerging that we can see in fish and likewise in all sorts of different animals, which I thought was I'm a professional mathematician. This is not my home territory, but I thought this was just really fascinating stuff.
I find that to be very interesting because this is a case where people or animals just can see a quantity without words. And it looks more as if it's not just remembering what it is, it looks at the size and the mass of something. So, does that tell us kind of what language does or doesn't do?
I think it's the starting point for what underlies the higher number senses. So
Sure.
we use spoken language, we use written notation. That's our way of accessing numbers. I think because, we've been doing that our whole lives, if we're people who live in countries where you have compulsory education from whatever early age, I think it's very difficult to get a sense of what is learnt and what is just innate. And actually, we have quite a good innate number sense. It's fuzzy, right? For at least for big
Right.
numbers, it's not. We don't have an innate sense of 22, right? But what we do have is the ability to make quite tight relative numerousness judgments. So the cutoff is for as an intelligent adult human is around about 10%. So if those two sets of coins I show you, if one is 10% bigger than the other, you'll probably spot it. If it's smaller than that, you probably won't. I mean, you might get lucky, but 10% is quite fine, right? So that's part of the innate sense of number that we have. And then things like spoken language, written notation are built on top of that. And they come out of the fact that what they really come out of is a desire to handle numbers exactly. So this innate number sense we have is good for exact numbers, up to 4 or 5. But if you want to handle numbers exactly beyond that limit, then you need some cognitive technology. And spoken language is the first one. And you really can't do it without that, or at least something equivalent to it.
Now, why does arithmetic enter spoken language so slowly and also so awkwardly?
So there are lots of people who speak traditional unwritten languages, so indigenous tribal languages, which have very, very limited numerical vocabulary. So people might have heard of the idea of a one-to-many counting system.
Yes.
So you see this in, for example, the Warlpiri language, which is an Australian Aboriginal language. And they have the word for one, they have a word for two, and they have a word for, well, we translate it as many. I mean, it just is a sort of general term for more than two. And the reason they have that system is that they've never had the need to develop anything more, right? I mean, their particular mode of life does not require any exact numbers beyond that point. So they live a hunter-gatherer lifestyle. I think a big change is once people started living in settlements with a more agricultural mode of life, then they found a need to develop a larger numerical vocabulary where you are handling numbers precisely up to a higher limit. And the thing which really changed the game really was the emergence of larger human settlements in the form of cities. And as soon as you got cities, just the different types of activity people did, and in particular the emergence of money, that was just a game changer. Because as soon as you've got money, you need a really good functional system, both spoken and written, for handling numbers. And it was really, money was really tied up to the emergence of early written numerical notation.
So, as we're going into civilizations, they don't necessarily abandon a number system when they fail, right? So, we started with Roman numerals, but now we're going into larger cities. We end up hacking them in a way. Now, what do these hacks essentially reveal about human problem solving?
Yeah, it's an interesting point, that, because when you think about Roman numerals are really quite rudimentary form of notation. I mean, they're a couple of steps beyond the Stone Age tally. The oldest written notation we have is just a tally stick, a bone with some notches on it, right? And Roman numerals are a bit beyond that, but only a bit.
Yes.
They're really quite basic. On the other hand, the Roman Empire was absolutely gigantic. It was the largest empire the world had ever seen. And they clearly had, there was money flowing in all sorts of directions, goods being produced on a large scale. So they had to have a really good sense of number. And the question I was wondering, how on earth did this enormous empire run on such a frankly feeble number system? And I think one thing which is not widely appreciated is that they had a slightly secret second system, and that was an abacus. Yes. So for actually calculating with numbers, Roman numerals are a nightmare, right? I mean, try doing long division with Roman numerals. I mean, this is just the stuff of nightmare. Well, quite. Don't try it. It's a horrible thing to try. On the other hand, if you learn how to use an abacus, then that's a tool where you can do these sorts of calculations really very quickly and efficiently. So I think the presence of the abacus allowed Roman numerals to survive longer than perhaps they otherwise would have done, right? Because people had another system for doing the calculation. They were calculating with the abacus, and they were just writing the answers with Roman numerals. But then, as you say, Roman numerals do run out at some point. The Greek numeral system is not so well known nowadays. It was a little bit more sophisticated than Roman numerals, but it also just caps out. It runs out. The largest in the sort of basic system, they had the symbol X standing for, well, mu, I guess, standing for a myriad, which is 10,000. That was the largest part of the standard system. So if you needed numbers bigger than that, you had to do the kind of sort of hacks and workarounds and extensions that you're talking about. And we do see some really, really imaginative and interesting things there. I think the most famous is a essay written by Archimedes.
I was just going to ask about that. So perfect.
Yeah. So it's if you're talking about big numbers in the ancient world, you've got to mention this. It's known nowadays as the Sand Reckoner. And it was actually a letter he wrote to the king of Syracuse, which is in Sicily where he lived, but that was part of the Greek-speaking world at that time. And the basic question he set out to answer was, how many grains of sand would it take to fill the universe? Which is just a wonderful, just imagine writing to the king about that. Isn't that like, why would you do that? It's just a wonderfully eccentric thing to do. I think part of the reason he did it, at least for my purposes, is to make a really important distinction between numbers which are just very big.
Yes.
And the concept of infinity. And I think there's a tendency, at least there was then maybe, for the two to blur into one another. I mean, once a number is just so big, we'll just say it's infinite. And that's not correct.
I was going to say, why didn't he ask about salt?
I don't know.
Come on, it's the most valuable thing. Archimedes?
Yeah, I mean, he could have asked about salt. There's another, actually even more outrageous thought experiment that was performed in ancient India by the Jains, who developed some really powerful theories of big numbers, and they did things with mustard seeds. So they built enormous, sort of mentally enormous towers of mustard seeds. I could talk about that if you like. But let's go back to Archimedes. So this he was making an important point, which is to some extent about the power of our number system, that it is capable of handling with total precision numbers far bigger than the ones which arise in the day-to-day course of things. And I think that's quite a powerful insight, actually. I mean, I'm not sure I think it's powerful enough to write to the king about, but Archimedes did. And so he did this thought experiment. And in some sense, the answer he got to the number of grains of sand needed to fill the universe is itself not terribly interesting, because he had a somewhat faulty picture of what the universe looked like. And the idea was that there was the sun in the middle. So he did have a heliocentric model, but then he had the fixed stars at the outside. So he had no idea of how big the universe is according to in a modern understanding. But what I think is quite fun is that, so as he went on, he had to extend the number system. The Greek number system was just nowhere near big enough to develop it, to express numbers of that size. So he had to, just as he was going, build a system for bigger and bigger numbers. And so his starting point was not the myriad, but the myriad. So a myriad is 10,000. So a myriad is 100 million. That was his starting point. And he worked in sort of multiples of 100 million and then powers of 100 million. But what I think is quite fun is he actually pushed the system enormously further than he needed for his thought experiment. So once he got going, he obviously, thought this was quite fun, and he kept pushing it, and he ended up and arrived at a number which, if we write it in modern notation, be 1 followed by 80 quadrillion zeros.
Okay.
Which is enormously bigger than he needed for sound in the universe, and that was where he ran out. And that's actually big enough that you're actually starting to see even our modern system of writing numbers is struggling with that, because I had to describe it. I can't give you a name for that number. Even just giving you the name for the number of zeros is perhaps stretching it, right? 80 quadrillion. I mean, not everyone knows what a quadrillion is.
A lot of zeros.
It's so a quadrillion has 15 zeros. So 80 quadrillion is 8 followed by 16 zeros. But then what he's talking about is a 1 followed by that number of zeros. And so it's an awful lot. And it's partly, I think, showing off, to be honest.
Yes.
But it's partly also just the joy of taking this stuff to a ridiculous absurdity, which I love. We see people around the world do that at various times, just dealing with numbers which are way bigger than any possible practical application, just for the fun of it. And I found a few examples of that, and it's just such fun.
Now, speaking of zeros, as we're on this topic, you argue that place value, not zeros, is the single most important numerical invention. Do you want to explain why?
Yeah, I think that's right. So, I mean, we take Archimedes as a jumping off point, because when you go through Archimedes' calculations, he's having to start. I mean, he's working with this Greek Ionic system, and that works so you've got symbols from 1 to 9, and then you've got a separate set of symbols for 10 to 90, and then you've got a separate set of symbols for 100 to 900, and then you've got a separate set of symbols for 1000 to 9000. That's the sort of basic system. And we see, so that's known as a ciphered system. It's basically an additive system, because you write down those symbols and you add them together, and that gives you the value. Now, we see systems like that emerge in a few different countries, different places around the world. But they've got a clear number of disadvantages. One is that as the numbers that you want to deal with get bigger and bigger and bigger, the library of symbols grows really fast, right?
Yes.
And it quickly becomes impractical. And especially as the larger numbers, people aren't going to use them very often, probably. These kinds of systems are not well suited to dealing with large numbers. Whereas if you compare that to the system we're used to now, which we call the Hindu Arabic system, it's only got 10 symbols, right? And we do see in a few different places in the world the same discovery being made, which is that you can recycle the symbols in an efficient way. So if I write down 33, those 2 3s have got different meanings, because the first one, the one on the left, doesn't mean 3, right? It means 3 10s, because its position is giving as much is as important as which symbol it actually is. And we're so used to that. I think with all these things, this is stuff you and I have known since we were 3 years old or whatever. So it's very difficult to see what a powerful and important discovery that is, because we're so used to it. But it is worth making the point that both the ancient Roman and the ancient Greek worlds failed to make that discovery. For all their impressive scientific discoveries of the ancient Greeks, and for all the incredible empire building of the Romans, they never made this discovery. But as soon as you make it, it allows you to express numbers of arbitrary size with total precision. And it's very, very powerful because not only can you express the numbers, but going back to calculating, we learned again at school methods for doing multiplication, division, addition, subtraction. Using that system, you line things up in columns and so on. And once you know how, it's not especially difficult. Compare that to Roman numerals. So I think having a system of that kind is really, I would say, it's an essential prerequisite to the modern high-tech age we live in.
There was an example from Maya civilization in particular, and it takes numbers to absurd temporal extremes. Do you think their notation invites cosmology, or is there another way around that?
Sure, yeah, absolutely. So I think so we're talking about the classical Mayans, who were people who lived in Central America between, I think the usual dates that are given to around about 250 to 900 CE. And the classical Maya made the same discovery that we've just been talking about. Namely, they developed a place value number system. So it's not the same place value number system we use today, which has its roots in India. It's a totally different system. It's actually a base 20 system. Ours is base 10. But nevertheless, they made that discovery. And having made that discovery, as you say, it suddenly becomes much, much easier to write down and think about very big numbers. Because, I can just write a string of 8s on a bit of paper, and suddenly I haven't done anything difficult, but I'm describing a number which is, potentially, bigger than the diameter of the universe or whatever. So I think to that extent, once you've got a number system which is so versatile that, it's just a question of writing a few simple symbols that immediately invokes gigantic numbers, I think it does encourage people to think on larger scales. I do think that's true. And boy, the Maya did do that. They really did. So they had a theory of time, which is extraordinarily involved, and I couldn't explain all of it. In particular, they had 3 different notions of what we'd call a year, right? 3 different closely related notions of a year, which they used for different purposes, and they used them all simultaneously for different purposes. But the one which they used for discussing really large time scales, nowadays we call the long count, the Mayan long count. And so it takes as its basic unit the day, or kin is the Mayan term for that. And then the next unit up is a 20-day unit. So roughly, we think of it as a month, but it's obviously not the same, which they called a winal. And then the notion of the year in this system is 18 of those winals. So 18 lots of 20 days, so that's 360. So that's the notion of the year in this system. But they also had notions beyond the year, multiples of the year. And everything from this point on is a multiple of 20. So there's this slightly weird feature in this system, which is that everything's a multiple of 20, except the one I just said, which is 18, right? So 18, quote, months in the, quote, year. But beyond that, everything's a multiple of 20. So the tun is the year. The next one up is the katun. So that's 20 of the years. So that's 7,200 days. And then the next one up on that is 20 of those, which they call a baktun. So that's 144,000 days, which is 394 solar years. So just shy of 400 years. And that's the basis of the system. So you see these dates written on Mayan monuments throughout the region. So it's five places. And these represent dates counting from a very specific day 0, which scholars have traced back as the 11th of August in the year 3114 BCE. That's the day zero in this system. And they use this 5-place system to date their monuments. It's the system they used to talk about their history, essentially. But what's interesting is that in some places we see dates which have got more columns. They've got longer, and therefore they're dealing with longer units. Each one 20 of the last one. So the next one beyond that is the Picton, which is now, so the previous one was just under 400 years. So 20 lots of that is taking us to around 8,000 years, a little bit less. And then they had ones which go beyond that as well. And you're starting to get into really seriously long timescales. And there's a place called Koba where archaeologists have unearthed a variety of monuments. And we see some which are the dates are extraordinarily long. So we see one where the date is followed by 4 zeros. And assuming this is configured in just an extension of that system, that's now talking about timescales on the scale of octillions. Right?
Oh my goodness.
So that's 10 to the 27, 10 with, or 1 with 27 zeros after it. But what's I think really interesting is that it seems like what they're using that for is to represent today's date, i.e. the date that this monument is being made. So rather than being a date in the far future, it's indicating that somehow the true base day zero is actually octillions of years in the past, which of course is far longer than modern physics tells us the universe is.
Absolutely. But on that very grand scale where we're seeing this exponential growth, even for timelines in our calendar, it changes to where growth actually turns dangerous, right? Large numbers, watching them explode to exponential growth. In that case, look at your calendar year. We can take examples of nuclear reactions, pandemics, debt, inflation. Why does this feel like such a tonal shift when we're making things exponentially grow?
Yeah, exponential growth is so central when we're talking about big numbers, because as you say, it arises. It's to start with, it's inherent in our way of writing numbers, and indeed in the Mayan way of writing numbers that we've just been talking about. Because if you think about, you write your ordinary number on a bit of paper, what do the columns represent? They represent ones, tens, hundreds, thousands, 10,000. That's exponential growth right there. So exponential growth is central to any theory of big numbers, in terms of writing them down, in terms of understanding them mathematically. But what I did also notice when I was asking the question, okay, where does exponential growth arise in the real world? And as you say, there's quite a number of cases where the answer are, well, really quite grim scenarios. So a pandemic is a classic example. If one person infects 2 others, and to take the COVID pandemic, that's an underestimate. Nevertheless, you get this sequence 1, 2, 4, 8, 16, which grows very, very fast, very, very quickly. And that's so the fact that the COVID pandemic, or indeed any other pandemic, starts in one corner, some village in some country somewhere, and sweeps the world in little time. That is testament to the power of exponential growth. Nuclear reactions are another. In a nuclear bomb, or maybe more positively in a nuclear reactor, it all starts with one. If we're talking about nuclear fission, then we're talking about one atomic nucleus splitting, and that triggers 2 others to split, and that triggers 2 others to split, and that happens with great rapidity. So again, there's exponential growth in there. I think the one that people agonized about a lot over the 20th century was human population growth. And of course, this is most famously discussed by Thomas Malthus, who was a 19th century economist. And his real fear was that, on the one hand, population grows exponentially. On the other hand, production of food, say, grows linearly. And as a result, in his reading of the situation, society, however technologically advanced it may be, is always going to hit a catastrophe whereby the population exceeds and then quickly far exceeds the available resources. And this was, an enormously powerful idea. It was an idea which really captured the imagination of Charles Darwin, and it was an important insight in his development of the theory of evolution. But of course, it also, I fear, led to some humanity's worst ever ideas once people started to really worry about this and say, okay, we've got to find ways to keep the population down. And, once you take that idea seriously, you're opening the door to some really horrendous ideas. As it happens, we are seeing now, we are in a stage now where population of the world is growing, but it is not, the rate of growth is no longer increasing. So it's not growing exponentially. So the global population at the moment is not following Malthus's fears, which is reassuring, I guess.
Now, I'm curious, is there at some point where exponential growth becomes irreversible? And how can we tell when we've already crossed that line?
I think it depends on the context.
Sure.
I think what I would say is, in the physical universe, wherever you've got exponential growth, at some point it's got to stop.
Right.
Really, because at some point you run into some fundamental law of physics. So if you've got things which are growing bigger exponentially, at some point you're going to just outgrow the planet or the universe. If things are getting hotter, at some point, you're going to break the laws of physics. So I think exponential growth can only ever be a short-lived phenomenon in the physical world. I mean, if you take the example of the pandemic or a pandemic, I mean, hopefully, we intervene and find ways to cure it or stop its growth or whatever. But even if we don't do any of that, it's just going to run out of people to infect, right?
Sure.
So,
or it mutates and develops and redevelops and.
Sure. So it changes
Right.
into something else. But just the original exponential growth cannot continue indefinitely. I think there's two possible exceptions to that in the physical world. One is the growth of the universe itself, which, so far as we can tell, and this is something physicists are discussing and theorizing about and arguing about, so this is not settled. But so far as we can tell, the universe we live in is growing exponentially, and is there doesn't seem at the moment to see any reason to think it's going to stop growing exponentially. And the other one was maybe a little bit niche, but it's maybe interesting to just mention, is finance. So finance is somewhere else we see exponential growth, because if you think of interest rates, so you think of a loan, it grows 5% a year or whatever. That's exponential growth. And inflation is exponential growth. And what we sometimes see in cases of, maybe 5% interest forever is feasible. If the value of the currency changes, then what we've seen people do is just revalue the currency. So we saw this in Zimbabwe at some point, where the number of zeros on the notes had got too much. So they just said, okay, we'll just chop off the final 6 zeros and just carry on from here. So you just redenominate the new Zimbabwean dollar as a trillion or whatever it was. I can't remember the exact number of the previous ones. So in finance, because there's no sort of physical underwriting of that potentially can carry on. But the growth of the universe itself is the other one, where potentially we have just indefinite exponential growth so far as we can tell. Though once you're speculating about the really, really distant future, it is speculation, but according to our best theories at the moment, it should continue.
And then in the book, you make a sharp turn from physical size to possibility space, right? And there's also things that are bigger than the universe. Can you go into that a little bit for us? And you also connected some of this to games like chess and Go, which make it kind of perfect for laboratories for huge numbers.
Yeah, absolutely. So I think the jumping off point for that discussion was, you know, try and extract some of the biggest numbers you can out of physics, right? And
Absolutely.
you think, once you've done that, you think, okay, these are like, so for example, 1 followed by 80 zeros, so 10 to the power 80, that's the sort of standard estimate for the number of atomic nuclei in the observable universe. And you think, okay, that's like a ridiculously big number. Surely we're never going to, in practical situations, we're never going to need any numbers on that scale or bigger. But actually, as soon as you start thinking about possibilities, you do get numbers on that scale, and indeed bigger. So chess is a sort of classic example. It's been studied for hundreds of years, of course, and as well as being studied by people who just love playing chess, it's also, in more recent decades, become crucial in artificial intelligence, of course. Can we get computers to play this game? And one of the first people who thought about that was a mathematician called Claude Shannon in 1950. And so his idea was to get a computer to play chess. And of course, in 1950, a computer was a pretty different thing to what it is now. But he outlined the scale of the problem, because the sort of obvious way of getting a computer to play chess is, well, I'll just think through all the possible different moves and I'll pick the best one, right? And if you're doing, noughts and crosses or tic-tac-toe, that's fine, because the number of possible moves is very small. But in chess, the numbers grow very, very big very quickly. So Shannon did some estimates that the number of possible board positions, and his estimates here, by the way, are not particularly subtle. It basically starts from just thinking, okay, imagine I've got a full chess set, and I'll just put the pieces on the board one by one at random. How many different configurations could there be? And then, okay, you have to fiddle it around, because pawns are all the same. So if you've got, if you swap two pawns, that's not really a different position. And there's some illegal positions, like having the two kings next to each other or whatever. So you have to massage it a bit. But nevertheless, I mean, the basic estimate is not a complicated thing. But his estimates were there about 10 to the power 43 different positions in chess. That's 1 followed by 43 zeros. That's individual positions. And of course, once you start counting games, so that's stringing positions together and to make a legitimate game, he estimated there around 10 to the 120, so 1 followed 120 zeros. So at that point, we're now way beyond atoms in the universe territory, and yet we're doing it by just analyzing a fairly, as I say, not a technically difficult analysis of a commonly played game. So these sorts of numbers are around if we choose to see them.
So would you say that this complexity depends on structure more than sheer size?
I think it's a combination.
Okay.
That a much simpler game than chess is the spelling bee, right?
Yes.
And a spelling bee, suppose I ask you to I give you spell the word Brobdingnagian, which is a word I like. It means if you don't know what that word means, it means enormous, right? That's why it's...
Yes, know what that word is.
Sorry, I should have given you the chance to say to claim the glory. Apologies. Yeah. So the reason I brought up the word Brobdingnagian is because it's a rarely used word. It's 14 letters long, and so it's the sort of word that might arise in a spelling bee, a spelling competition. But the point is that if you wanted to estimate the sort of possibility space. So that's a 14-letter word. So you've got, what's the possibility space? Well, there's 26 possible letters you could guess for the first letter, 26 for the second letter, 26 for the third letter, and so on. So it's just 26 to the power 14, which is a very big number. It's 10 to the power 20. so even in this situation, we've got a very, very, very large number. But the point I'm making here is that the spelling bee is obviously a game of great skill, but it's not a game of strategic depth, right? I mean, you either know how to spell the word or you don't. And if you guess the first letter wrong, you're done. So there's no tactical complexity to the game. So strategically, it's a very, very simple game, unlike chess, which is strategically very complicated. So the point I'm making is that having very, very big numbers, sort of underwriting the possibility space I would say it's a necessary prerequisite for a strategically complicated game. But in and of itself, that's not enough, right? Because the spelling bee has also got these very large numbers underwriting it.
One thing that we haven't mentioned really, we touched a little bit at the beginning of this interview, was about mathematical logic. And one point you talk about Goodstein's theorem, and it kind of feels like a philosophical gut punch. It's a true statement about ordinary numbers that can't be proved. Tell us about it, and why is that so unsettling?
Yeah, I think it is somewhat unsettling. It's just maybe to add a little bit to that. It can't be proved from the usual axiom system that we use for arithmetic. So the usual axiom system was, as I mentioned earlier, it was developed by this Italian logician in the 19th century called Giuseppe Peano's, called Peano's axioms. And people have tinkered with it ever since. But basically, that remains the starting point. If what you want to do is write down the sort of fundamental list of rules that make arithmetic work.
Sure.
And I guess the real gut punch was delivered in 1931 by Kurt Gödel. So this is his famous incompleteness theorem. And what Gödel proved was that Peano's axioms are not enough to deduce all true statements about arithmetic. So there will be true statements about arithmetic which cannot be proved from Peano's axioms. But actually it's worse than that, because you might just think, okay, all that means is that Peano's axioms aren't quite enough. We have to expand and build a bigger system or whatever. But no, because what Gödel's theorem says is no axiom system you can write down will ever be enough to deduce all true statements about arithmetic. And that, I think gut punch is exactly the right term for that. It's really a bit of a shock to the system. I think it's a very famous theorem, right? I mean, I think
yes,
a lot of people would have heard of Gödel's incompleteness theorem, even they couldn't tell you the first thing about it, right? They've heard those words.
Everyone's heard of it.
Everyone's heard of it. And I think it cast mathematics in a new light, because there was at that point a hope which was expressed earlier by David Hilbert, who was one of the biggest names in maths around the start of the 20th century. What he hoped would be, for centuries, maths has worked by just making sort of incremental progress on these big ancient problems. Someone works incredibly hard and drives things forward an inch, and maybe some theorem is proved, but then that opens, he was hoping for some real sort of final knockdown victory in mathematics.
Yeah.
Something which would just allow us to just deduce basically everything we needed to know about numbers, just like with a click of the fingers. That's what Hilbert hoped for. And it was Gödel's theorem which really absolutely knocked that idea flat. I mean, we could never possibly hope to do that because Gödel's incompleteness theorem basically kills it. And what that means is that maths has continued really in that same sort of laborious way as previously. We're still, making incremental progress because that's the best we could do, right? And that's likely to be the best we will ever be able to do. Okay, so none of this is to do with big numbers so far. So the big numbers and Goodstein's theorem enter the picture once we start asking the question, okay, so what are these true facts about numbers that can't be deduced from the usual axiom system? So I'll just take Peano's axiom system as the standard one. But you could replace it with logicians that have built many others and everything. It's true for the others as well. But let's stick with the standard one. And for a long time during Gödel's work and after it, all these true facts about numbers that couldn't be deduced from the axiom system had a very sort of artificial feel to them. They were clever bits of logical trickery. I mean, it comes down to sort of classical paradoxes like this statement cannot be proved. And you think about that and you realize it can't be proved, right? And it's very clever. And it's really ingenious. But at the same time, it's not the sort of thing which, if you're just interested in studying numbers because you're interested in prime numbers or, some classic mathematical topics, you think, well, that sort of stuff's never going to arise, right? So maybe I just don't have to worry about Gödel's theorem at all. And Goodstein's theorem was probably the first example of a theorem which it's in that Gödelian position, right? So it's a true statement which can't be proved from the usual axiom systems. On the other hand, when you look at it, it's not clever logical trickery. It doesn't, on the face of it, have anything to do with logic, right? It's just a statement about numbers. And that's the importance of Goodstein's theorem. It's the first example of what we call concrete incompleteness, i.e. Gödelian incompleteness, but of a much more concrete kind, which is understandable and accessible and of interest to people who don't know anything about logic. And it also involves some really, really gigantically large numbers, which is why it fits into this story. So it's Goodstein's found a way of describing a sequence of numbers. I think the key thing is not the recipe, it's the sequence, right?
Yes.
And so the sequence, it starts as with an input and it gives you an output. And the recipe is just using ordinary facts about numbers, okay? And it's using them in a clever way, but it's just using ordinary numerical properties. It grows very, very fast. So, for example, on input 2, it outputs 4. On input 3, it outputs 6. Okay, so far so good. On input 4, it outputs a value which is bigger than 10 to the power of 100 million. So 1 followed by 100 million zeros. On input 5, outputs a value which is bigger than 10 to the 10 to the 10 to the 10 to the 4. So,
okay.
So we're starting to get numbers which are really tough to write down. You have to have a tower
notation.
of powers.
Yes.
Yeah. So you have to develop some new notation. And actually, on input 6. Even if I was to sit here and go 10 to the 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 10 to the... I couldn't say that enough times. That's just the number of times you have to say it is too many.
Sure.
And that's why you need to develop new notation, right? So that's just on input 6, right? And it keeps growing ever, ever, ever faster. So this is a sequence which grows massively faster than exponential growth, right? We think of exponential growth as being the sort of byword for really, really fast growth. But
Absolutely.
This is far, far faster than that. And actually, the key thing is that it grows too fast for Peano's axioms to be able to handle. It's just the growth is too out of control for our usual laws of arithmetic to handle, which I thought was quite striking, right? It's big numbers strike again.
Yes. Now, I'm curious, as we're wrapping up here, for listeners or viewers, what is one thing that you want them to take away from, I'll say, huge numbers or big numbers?
I think that it's that they strike in any given scenario. So whatever context you're working in, if you're building a computer system, then the question is going to be, how powerful a computer can you build? What's the fastest you can make it run? What's the biggest memory capacity you can build, and so on? I mean, in driving forward any kind of human endeavor, we're always trying to push things further. And that's telling us what big numbers mean in that context. And that changes over time. So in the context of technology, what's a fast computer now is a lot different to what a fast computer was 50 years ago. Quantum computing
Quantum computing from AOL dial-up in the 90s.
Absolutely. Or and you can go even further back and go to punched card computers back in the 19.
I don't think our audience, some of the younger listeners, will ever know that. I have a rotary phone in my house,
Oh,
okay?
wow.
I have one of the original ones that don't even have a dial for a party line.
Oh, gosh. Right. I mean, I
Uh,
remember rotary phones, but I
yep.
didn't keep mine. I think this is part of the same story, though, which is that, the things which seem now, we're talking about these things, they seem like from another world. It's only a few years ago
It's only a few years ago.
and things keep growing and improving, and the things that we use now and think are super high tech are going to seem, like Flintstones contraptions in another 50 years, potentially. And I guess that's part of it, which is that our horizons are ever expanding, and they should be. That's what we want to do. We want to look further into the horizon, and I think big numbers in whatever context you're working give us the vocabulary to phrase that.
Huge numbers have a way of humbling us, not because they're flashy or dramatic, but because they quietly expose the edges of our thinking. And they show us where intuition runs out, where language strains, and where even our most powerful symbols start to crack. What huge numbers reminds us is that mathematics isn't just about counting bigger and bigger things. It's about understanding systems where we've built to make sense of our world and recognizing the moment when those systems fail. Those failures aren't bugs, they're features. They tell us something profound about what it means to be human, trying to grasp a universe that refuses to fit neatly inside our heads. If this conversation made you rethink what big means, I strongly recommend checking out the book Huge Numbers. Always remember, stay curious and stay informed.